So, in today's lecture, we are going to learn a little bit about magnetism, magnetic susceptibility, and we are going to calculate the magnetic susceptibility of two systems. So, let me first explain what these two systems are, then I will define the magnetic susceptibility and how it is calculated, and then we will go further and calculate the magnetic susceptibility actually for these two systems. So, let us try to understand what these two systems are. So, the system on your right is a magnetic insulator. So, here you have a material where every lattice site is decorated with a spin half, one half. So, you can think of an electron sitting at every lattice site, one electron, one spin half sitting at every lattice site. So, if you zoom in any little region, any little volume of this material, you would see this nicely arranged array of spins. The spin-spin interaction is assumed to be 0. We assume that the spins do not interact with each other, the interaction is 0. So, at any temperature T, if you take a snapshot, you would see that these spins are arranged in a random manner. What that means to say is that if you calculate the magnetization of this sample, magnetization is defined as the net magnetic moment per unit volume, that magnetization will turn out to be 0, because there is no specific orientation along which the spins are pointing. They are oriented in random manner. And if you, so that is the snapshot at any time. If you take a second snapshot after a time delta t, what would you see? You would see a similar situation, not exactly the same situation. The spins would have turned changed their orientation, but overall the net magnetization will still be 0, right? Because why? Because the spins are in a state of constant thermal agitation. So, their orientation is constantly changing, and that is happening to all the spins, and the net magnetic moment is 0. Okay. So, this is my system number 1. So, remember at each lattice site there is a spin 1/2, and the total number of lattice sites is n. So, which means that the total number of electrons are n, or total number of spins are n rather, right. So, we have n spin half particles in this system. We are going to compare this to a system which is the system that we are working with these days, the current module, the degenerate Fermi gas of electrons, and here again we have n electrons. The difference is that in this system these n electrons are in this form, they are completely delocalized, the electrons are just going around, it is a gas of Fermi gas of electrons, and in this case the electrons are highly localized. At every lattice site there is one electron, and the electron is not going anywhere, only its spin is changing its orientation, its position is fixed. In this case the electron is delocalized, it is going everywhere, it is exploring the entire lattice, right. That is the essence of saying that it is a gas. Now, if we once again here also, in the absence of any applied external magnetic field, the net magnetization should be 0, because there are as many spin up particles as there are spin down particles, right. So, the total orientation has to be, that magnetic moment has to be 0. So, for both the systems, the magnetization is 0 in the absence of a magnetic field. There is no spontaneous magnetization, that is because there is no interaction between the spins, right. If there is an interaction between the spins, then you get ferromagnetic ground state or antiferromagnetic ground state, right. That comes about when there is an interaction between the spins, but we have assumed that they are non-interacting. Okay. So, since they are non-interacting, Therefore, there is no spontaneous magnetization, which means that there is no magnetization in the absence of an external magnetic field. Now, when you apply a magnetic field, what happens? In the presence of a magnetic field, you have to start thinking about it physically. What will happen if you apply a magnetic field to this system? So, when you will apply a magnetic field, the magnetic field is going to, make them align along the field direction, because each magnetic dipole will experience a torque, right? And that will try to orient this dipole in the direction of the magnetic field. Okay? And what would the temperature do? The effect of temperature is completely opposite. The temperature is trying to randomize the spin orientation, right? So, it will be a kind of fierce competition between the applied magnetic field and the thermal energy, the magnetic energy and the thermal energy. Okay? The magnetic field is trying to orient them along the direction of the field, and the temperature is trying to randomize them. All right. Same thing is going to happen over here, isn't it? You have spins. These electrons have spin 1/2 or minus 1/2 along the field direction, the projection of the spin. And this system will also acquire some finite magnetization when you will apply an external magnetic field. The question I am asking is, in which of these two systems the magnetization will be more for a given temperature and for a given magnetic field. We have understood the two systems. That is a localized system, and this is a delocalized system. The number of spin half particles are same in both the cases. The only difference is here you have delocalized and there you have localized. So, we are going to answer this question during this lecture. Yeah. What I mean by insulator is that these electrons, their positions are fixed. They cannot. So, if you apply an electric field, you are not going to move them, right? So, maybe these electrons are bound to the nucleus and they cannot leave the nucleus, right? On the other hand, in this case you have delocalized electrons, as in the case of sodium, for instance, the 3s electrons of sodium, right? Is this clear? The problem is that sodium has 11 electrons, right? So, one of the electrons gets how many electrons are there in sodium? I do not know. Total 11 is there, right? So, the 11th electron is the itinerant, is the delocalized electron, but the remaining 10 electrons that stay with the nucleus, okay, because their number is even. So, their spin and angular momentum, everything get cancelled. So, therefore, there is no spin at the lattice site in sodium, right. Whereas, if you take the case of some material where you have a uncompensated spin 1/2 at each lattice site, then you have this kind of arrangement. So, the susceptibility is defined like this. Susceptibility is defined as magnetization divided by the applied magnetic field in the limit h tending to 0. Okay. So, for these systems actually it does not matter, would not matter much if, unless the field is very high. Why? Because for these systems, as you would see, that the magnetization when plotted against field is fairly linear up to reasonably high magnetic fields, and eventually of course the magnetization is going to saturate. So, so basically non-linearity sets in at high fields. So, we define susceptibility as the slope of m versus h plot at h equal to 0. Yeah, h equal to 0. That is how the susceptibility is defined. So, this is magnetization, applied field. Now, coming back to the electron. So, when electron has a spin 1/2, its magnetic moment is given by minus g s mu b, where g is the Landau-G factor, which is 2 for an electron, s is 1/2 and mu b is Bohr magneton. So, therefore, the magnetic moment of electron would be minus mu b when the spin is plus 1/2. So for spin plus 1/2, the magnetic moment is minus mu b, which means it is pointing downward in the downward direction. For us, positive sign indicates vector quantities pointing in the upward direction, negative sign indicates quantities pointing in the downward direction. So here we are going to apply a magnetic field in the upward direction. Okay. So this is minus mu b, and when the spin is minus 1/2, then because there is a minus sign in the formula here for the magnetic moment, therefore you will get a plus mu b magnetic moment. Okay, the magnetic moment is plus mu b. Now let's define mu b. I said mu b is Bohr magneton, and this is how it is defined. Mu b is the magnetic moment associated with the electron, associated with the orbital motion of the electron in the ground state of hydrogen atom. Okay. So here is your hydrogen atom. There is a proton at the center, and there is an electron which is going around. Okay. We calculate the magnetic moment associated with the orbital motion. So the magnetic moment is given by current times the area of the loop, right? Area of the loop is the area of this orbit, and if r is the radius of the orbit, then the area is pi r square, and the current I is charge divided by time, right? And the time is the time that the electron takes in completing its orbit. So that will be E divided by tau, right? We have put minus E because of the negative charge of electron. Now tau is the time period that the electron takes, the time that the electron takes in completing its orbit. You can write tau as r divided by v, right, where v is the speed with which the electron is going around. Okay. Now, as I said that we are calculating the magnetic moment in the ground state. Now, you know from Bohr's model that in the ground state of hydrogen atom, the orbital angular momentum is h bar, right, that is the value for L. So mvr is equal to h bar. So you can plug in the values of Vr, eliminate it, and use this in this formula. Use tau equals to r over v, and then put Vr in terms of m and h bar, and then this is what you are going to get for the magnetic moment in the ground state. Okay. So this is the definition of Bohr magneton. So mu b then is E h bar by 2m. Okay. So that's the formula for mu b is equal to E h bar by 2m. Okay. So once again, when spin is plus 1/2, the magnetic moment mu on the electron is minus mu b, and which means it is pointing down, and when s is minus 1/2, the magnetic moment is plus mu b, which is pointing in the upward direction. Okay. Now when h is 0, h is the applied magnetic field. When h is 0, the number of electrons whose movement is pointing up is equal to the number of electrons whose movement is pointing down, and this is equal to the total number of electrons that you have in the system divided by 2, right? And therefore, the magnetization is 0. There is no net magnetization, right? Now, what's going to happen when you will turn on the magnetic field? So, in the presence of a magnetic field, these two levels, these two up and down degeneracy is going to get lifted, right? Why? Because in the presence of magnetic field, as I explained earlier, the magnetic moment want to line up with in the direction of the magnetic field, right? So the energy of the movement in the direction in the presence of, so you can write the Hamiltonian, and this is minus mu dot h. Okay, so I'm maybe it is confusing. So just let's just write U for the energy. So this is the magnetic energy. Mu is the magnetic moment, and H is the applied field. Okay. So this will be, so you know H is applied in the upward direction, right? And mu is, when mu is also pointing in the upward direction, the total energy will be minus mu BH. Okay. So this energy will be minus mu BH for the magnetic moments pointing in the upward direction, or for the spins pointing in the downward direction. All right. So for spin orientation, I am using this yellow color. So when the spin is pointing down, sorry, the spin is pointing up, plus 1/2. The magnetic moment on the electron is pointing down. When the spin is pointing down, the magnetic moment is pointing up. Okay. Okay. So this orientation is not for the spin but for the magnetic moment. Okay. And similarly, this energy will be plus mu b by h when the moments are pointing in the downward direction. Plus mu b h when the moments are pointing in the downward direction. Okay. So therefore, this is how the degeneracy is going to get lifted. So this energy is minus mu bh. This is lowered, and this energy is plus mu bh. This above, measured from this level, is the neutral line, right? So this is minus mu bh, and this is plus mu bh. Okay, is that fine? Now at any temperature T, how will you decide? Now it's a problem of classical statistical mechanics. At any temperature T, what should be the population of this level and what should be the population of this level? That will be given by the Boltzmann factor, right? So the so this is the energy of the electrons that are pointing up, the movement pointing up, and their movement is pointing down. These are aligned with the magnetic field, these are anti-aligned. And when the temperature is high enough, very, very high, and the field is not very strong, then you will have fairly large number of sites that are found in this state as well as in this state, right? So you are not very different from this situation if the magnetic field is not very strong and the temperature is not too low. Okay, you will see that in a minute. So if I have to write what is n up, so n up, that would be how much? N exponential minus and minus will become plus. It is right, plus mu b h by kt divided by exponential mu b h by kt plus exponential minus mu b h by kt. That's for n up, and similarly for n down, you can write a similar expression, except that here you will get minus mu b, right? So for n down, yes, yes, yes. Why? Because this was E minus delta by kT, right? So this is then n exponential minus mu b h by kBt divided by the same denominator which we have over here. Okay, so then the net magnetization will be the difference of these two. So this minus this, okay, that will be delta n. This is when h is 0 and when h is non-zero, then you have your delta n equals n up minus n down, and this is equal to n times this minus this. Okay, so it will be exponential minus exponential minus box is mu bh by kBt plus box divided by exponential minus box plus exponential plus box. Okay, and this is nothing but tanh of box. So this is n times 10 hyperbolic mu b h by kb. Okay. Now what will be the magnetization then? So when h is non-zero, you got a non-zero value of delta n, unlike the case when h is 0. That means you have a non-zero magnetization now, right? So the magnetization that your sample has acquired now will be given by mu b times delta n, isn't it so? So this will be then, you plug it in here, so you'll get n mu b and then tanh of mu b h over kBt. Okay, now let's find out the susceptibility chi. Chi is m by h in the limit h tending to 0, right? So in the limit when h is very small, so the argument of tanh is very small. So in that limit, tanh of x is just x, right? So therefore this will become n mu b square h over kBt, and h will get cancelled out because you're taking the dividing by h. So that's your susceptibility. So what do you learn? What have you learned? What you have learned is that the susceptibility follows a 1 by T temperature dependence, right? The susceptibility is going to increase as you decrease the temperature, and it will tend to infinity when the temperature will tend to 0. Does it make sense to you? Does it make sense to you? Theoretically, does it make sense to you? It does make sense because at zero temperature, this energy gap is too large to overcome thermally. There's no thermal energy available, right, at zero temperature. So therefore, the entire population will descend into this state. They all will have their spins pointing in the upward direction. The sample will get completely polarized even for a tiniest magnetic field. Even a tiniest of field will polarize the entire sample. Why wouldn't it? It would, because there is an energy gap that separates these two states, the up state and the down state. And in order to explore both the states, you need thermal energy. If the thermal energy is not there, then the system will choose the ground state, the lower of the two states, which means that all the magnetic moments will just line up in the direction of the field, no matter howsoever feeble the applied field is. Even for the tiniest of fields, the magnetic moments will line up, right. But as you increase the temperature, what is happening? The susceptibility is dropping, and dropping rather fast. Why it is dropping? Because as you are pumping in energy, thermal energy, this state will start getting occupied. So, the difference n plus minus n minus will start diminishing, right. This difference is n plus minus n minus is equal to n when the temperature is 0, because there is nothing here, and as you are increasing the temperature, you will start populating it. And if you go to very high temperatures, very high temperatures, what will happen? What is going to happen is that your temperatures kBT is very high compared to this energy gap, right. The system will not even see this energy gap. For the system, the energy gap does not exist, because of energy available. For instance, if you are traveling in a Land Rover, which has a huge tires, you do not even care about little pebbles, right, do you? No. So, that is what is going to happen. I mean, this is like a very tiny energy gap in that case, because the thermal energy that you have is huge. So, this actually is called the Curie law, and this is called Curie. Okay. So, what we learned then is that chi as a function of t for this system, for the localized system, does like this, right. So, it goes as 1 by t, and it should it should make sense to you. I mean, you should be able to come in terms with it. Why does it do this? Because there is a fierce competition, as I stated before, between the magnetic energy and the thermal energy. When thermal energy wins, you are here. When the magnetic energy wins, you are here, right. So, this is how the susceptibility of a localized system would behave in the presence of course, you have to apply a magnetic field. So, this is the localized system, localized electrons. At each lattice site, there is a spin 1/2, which is not going anywhere, right. Now, let us come to this part of the board and see what happens here. What is your guess? At any temperature, if I fix some temperature T, the susceptibility for localized system is this much. On the same graph, I have not yet calculated it, but I am just trying to see what your intuition is saying, telling. On the same graph, when I will plot the susceptibility of this system, remember it has the same number of electrons, exactly the same number of electrons, n 1/2 particles, just as there. Where do you think this will come? Will it be below it? Will it be above it? Will it be very far above it? Or will it be very far below it? Let us try to. Huh? Yes. 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 Okay, let us see. So, before I do this, let me just remind you a couple of things that we did already. So, one of the things is that here we defined a quantity d, which is called the density of states, right. Do you remember density of states? So, dE goes as square root of E. This you know, yesterday also we did that, right. So, if you plot dE versus E, it looks like this, right. Density of states, what does that mean? you know, it's what that means. It makes sense only in the reciprocal space. In the reciprocal space or the wave vector space, you have this qx, qy, and qz. These are quantized using the periodic boundary condition, and at 0 temperature you get a Fermi sphere, right? All the states inside are filled, states outside are empty. There are states all over, but the states inside are filled, the states outside are empty. This is your Fermi sphere. So the quantum states inside are filled, outside are empty. Right. So at 0 temperature, you get this EF. Right. Now here is a point, and next to it is another point. What has changed? The quantum number has changed. The quantum numbers are qx, qy, qz, and the spin quantum number, isn't it? At any point, you have qx, a certain value of qx, a certain value of qy, a certain value of qz, and you have two spin orientations at every point, right? Spin plus 1/2 and minus 1/2. So this is the total density of states. Density of states meaning, so how many states are there? These are how many states? Two states, two quantum states, one for plus 1/2 and another for minus 1/2. So what I am going to do is, I am going to first of all turn this plot. So I am going to put E energy on the y-axis, and I am going to put the density of states on the x-axis. So this is my total density of states dE, and this parabola is going to look like this. Is that right? Now suppose let me draw it a little bit. Look like this. Okay. Suppose I plot only the density of states for the up electrons. What would that be? So what I want to plot here is, I don't want to plot total density of states. I want to plot density of states for electrons with their spin pointing in the upward direction. So that will be how much? That will be 1/2 of this density of states, won't it be, right? So therefore, whatever, so for any value of E, so the total density of states is this, then for the same E, the total density of states in this case will be half, so it will come here, right? Similarly, for this guy, the total density of states is this. So for this energy, you just half it, so it will come here, right? And so on. So what I'm plotting here now is this parabola. This is 1/2 dE, and this therefore gives me the density of states of electrons with their spin up. So this is for spin up. Similarly, I can have 1/2 dE on this side for the electrons with the spin down. Okay. So 1/2 dE, and this one on this side. Okay, so this is for the electrons with the spin s down. So this is for s, for the spin of electron, spin up and spin down. And let's say the Fermi energy is somewhere here. Okay, so I can erase this, the total density of states. the combined, the joint density of states from both plus half and minus half. I have just separated them. Right? It's fair enough. I mean, makes complete sense. I have not really done anything which is very subtle. I mean, I just wrote dE as half dE, half dE, one half dE for the up charge pointing electrons with the spin up, and another one half for electrons that are pointing down. Right. Now, this is the situation when H is 0, no magnetic field applied, and since there is no field applied, therefore, the number of electrons that have their spin pointing down is equal to the number of electrons with their spin pointing up, and therefore, the net magnetization is 0, as it should have been, right. And remember, this picture is at t equal to 0. I am just trying to take a simplified approach at 0 temperature. This is the situation. Now, sitting at 0 temperature, if I turn on the magnetic field, what will happen? What's going to happen is that the electrons whose spin is pointing down or their magnetic moment is pointing up and the field is also pointing up, so their energy will come down because they are pointing in the same direction as the applied field. They are pointing in the direction of the applied field. So, therefore, their magnetic energy will come down, they will lower their magnetic energy. Whereas, the spins that are pointing up, their magnetic moment is pointing down and the field is pointing up. So, what will happen to their energy? Their energy will escalate because they are pointing in a direction that makes magnetic field very unhappy, isn't it? Magnetic field wants them to apply to turn in the direction in its direction. So, in the non-zero field, how is this diagram going to change now? Okay, let's plot it here itself. Okay, yeah, let's try to do it here itself. So, what did I just say? These guys have their magnetic moment pointing up. The field is also pointing up. They are in a very happy situation. They will lower their energy. In the presence of magnetic field, their energy is going to lower, which means that this whole curve is going to come down by an amount equal to mu b h, right. So, this side will then become like this. On the other hand, these guys, their energy is going to go up by the same amount. All right. So, you will have now this was your Fermi energy, and now what has happened is that you have this guy coming here and this guy coming here. This is actually highly exaggerated. I mean, even with a very large field, this shift is going to be minuscule compared to the Fermi energy. Fermi energy is of the order of few electron volts, and this mu b h would be a very weak effect, but I've just magnified it for you. So, what is this gap? This has gone up by an amount minus mu b h plus mu b h. This has come down by an amount. So, this gap then will be twice mu b h. Right? And what is the population difference? So, basically, the population difference between up and down is approximately this double hatched region, right. And what is the number of electrons in this region? N. So, that delta n, so that delta n would be very approximately, that delta n would be this area, and this area is this distance, the distance from here to here, you know, is how much? This is DEF, isn't it so? 1/2 DEF, right? And this is 2 mu b h. So, therefore, the number of electrons in this, the population imbalance between the up and down is just 1/2 DEF times the width of this rectangle, which is 2 mu b h. Okay, so 2 and 2 gets cancelled. So, this is what you get for delta n, and therefore, now the system will acquire a net magnetization because of the population imbalance that you have created. Earlier that imbalance wasn't there, but now it is there, and this much is the imbalance, and due to that imbalance the magnetization that you are going to get will be mu b times delta n, as we did over there, mu b times delta n. So, mu b times delta n would be how much? Then it will be DEF times mu b square times h. And so, what is the susceptibility of this system? What is the susceptibility of this system? Chi. Chi is m by h. So, that is nothing but the density of states at the Fermi energy times mu b square. Now, you know, you remember from previous lectures that DEF is nothing but 3n by 2 EF, right? We had proved this identity. So, we can plug that in over here. So, then it will get 3n mu b square by 2 EF. So, that is the expression for the susceptibility of a free electron gas, degenerate free electron gas, and this is known as Pauli paramagnetism, because it was first calculated by Pauli. Of course, he did not use this shortcut, I mean this hand waving argument to estimate, but you know, a more detailed calculation will give you approximately this result. So, what did we learn here? So, first thing that you notice here is that there is no temperature dependence, right. You may say that that is not surprising because the calculations are done at 0 temperature, isn't it so? I calculated the susceptibility at 0 temperature, no? Fine. Let's and we also know that at 0 temperature this is going to diverge. This is going to be a very large number, but this is a finite number, at least this much difference we see, right. But if we do a more elaborate calculation at non-zero temperature, which means that we allow for this to be not straight, but you know, this to go like this, in which case we will have to do integrations as we did in the case of specific heat. You remember how we calculated the specific heat? It was 3 times I had to erase the board to calculate the specific heat. You can do the same thing here. You can calculate the susceptibility. It is more elaborate. You have to, you know, take the you have to basically find n up and n down, and any of these is nothing but, you know, integration of FE, DE, FE and then DE, DE, and then you integrate it from 0 to infinity, and this will be 1/2, and then you have to change E by E plus mu b h, and similarly for n down you will change E by E minus mu b h and do the integration and do it. It's, I mean, it's not that difficult. You can, you know, do that. So, at finite temperatures, the only change that you will get is that this expression will change to this. Chi Pauli at a non-zero temperature is 3n mu b square by the way, this EF can be written as KB TF. Looks a bit nice. Twice KB TF. So I'm going to write that here. Twice KB TF and then 1 plus, sorry, minus 1 minus, and then you have pi square T square over 12 TF square. So that is the correction term that you get. That is the temperature dependence. So at room temperature, this is of the order of 10 to the power. Room temperature is, let's take room temperature to be 100 Kelvin to make life simpler. So of course it's too low, but 100 ka square is 10 to the power 4. This fellow is 10 to the power 4 already. 10 to the power 4 ka square is 10 to the power 8. Isn't it? TF is of the order of 10 to the power 4. So therefore this correction term is already 1 by 10 to the power 4 at 100 Kelvin. So you can imagine that this is a very weak temperature dependence, right? So therefore, for all practical purposes, the Pauli susceptibility is temperature independent. That's the first point that we note, that the temperature dependence is very, very weak. So for all practical purposes, you know, you can say that Chi Pauli is temperature independent. Unlike Chi Curie, which is strongly temperature dependent. Temperature independent. That's point number 1. Okay, that's point number 1. Point number 2. So if I drop this term, because this term is already 1 by 10 to the power 4. So if I remove it, then Chi Pauli is essentially what we calculated, isn't it? This is the prefactor. So Chi Pauli can be written as, is for all practical purposes, Chi Pauli is just this. So this I can rewrite it as n mu b square by kBt. I'm multiplying and dividing by t over here. Then you will get, along with this, 3 by 2 t over tf. Is this clear? 3 by 2 is put here in the bracket. Now what is this? Chi Curie. So Chi Pauli is equal to Chi Curie times 3 half T by Tf. Now you have the comparison. Now tell me which is bigger. Which of the two is bigger? Chi Pauli is very, I mean, it's very small because Tf is a very large quantity. So at 100 Kelvin, for instance, at 100 Kelvin, this will be 100, this will be 10 to the power 4. So Chi Pauli is 1/100th of Chi Curie at room temperature, near 100 Kelvin. But if you go down to 0 temperature, close to 0 temperature, this difference is going to be humongous. So for instance, at 1 Kelvin, this is 1, this is 10 to the power 4, right? So therefore, Chi Pauli will be 1 by 10 to the power 4 of Chi Curie at 1 Kelvin, as small as this. So if this is your Chi Curie, then Chi Pauli will be somewhere here. And it's temperature independent, doesn't depend on temperature. This is Chi Curie now, and here is Chi Pauli. Okay, so we stop here unless you have questions. Sorry, this factor here, because I took this multiplied by t in the numerator and denominator. So this become kBt and this become t by tf. So if you like this t and t, you can cut them. So it will be then 3n mu b square by 2 kBtf, which is the result that we derived.